Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Easy Learn. And here, this is the introduction to electronics. And we are discussing the previously continued topic in today's episode, that is the electromagnetism. Magnetism and then electromagnetism, then the forces of the forces acting on the magnets. And this is the relevant. And now we are going to discuss, for example, there is a magnet and a current carrying conductor is placed under the influence of the magnetic field, and then what force it will experience either on which side, and the intensity of the force, high, low, and much more, and all these things and related to the force will be discussed in today's episode. So let's start today's episode. First of all, and let's take the look at these magnets. If any, this is a magnet north south, and all the direction of the lines looks like from north towards south, and it completes its directions in this way. I'm not here very good for the drawing, but I just want to say that these are just a line coming from north towards the south. But if the magnet and if this magnet is brought near to another magnet, and this comes under the jurisdiction of another magnet, and the both magnets are bring close enough that they experience the force of attraction or repulsion of each other, then definitely the magnetic field pattern will be changed. Like in this case, the both magnets are brought near each other, and you can see this area is affected and the new pattern is discovered. And same is the case if the two magnets north south are bring in front of each other, and these are the parallel case in the front. This is just, for example, a case for the in this case. There are many cases which can be explained in the previous episodes, and I displayed and showed you many pictures there, and this is one of them. I take it from the previous episode. This is not the new picture here. So this is also disturbed is this case. It means that also in the case of the solenoids, if this is a solenoid and if I connect it with positive negative, this is of course it will produce magnetic line of the magnetic field is produced around it, because we know that whenever there is a current carrying wire, this is a simple wire which do not contains any current, but when I connect it with the source positive negative, and current starts flowing through it and aligns up in the direction, then definitely there will be magnetic line of the forces will be created, and the direction will be depend upon the source which we connect positive and negative with the direction of the current, and so on. This is the current. This magnetic field lines around magnetic field that is produced around this current carrying wire is basically due to the electric current that is flowing into the wire, and this is very small, and this is generated automatically when the current is flowing through the wire, and it depends upon the intensity of the current. If current is small, then definitely the magnetic field produced around it will also be in small quantity, but its intensity is increased up to some extent if the wire upon the material of the wire and the intensity of the current and other factors also, for example environment and to so on. But right now I just want to say that whatever if I increase the intensity up to certain extent, but if I said that I am going to apply an external magnetic field here and want to take a look and analysis on the force on a conductor in a magnetic field, then I am going to ignore this. So this is one thing you must need to be take into account before further proceeding, that I am going to consider the magnetic field that is provided externally, and forget about this one. This is the internal magnetic field. You don't need this anymore. This is very less as compared to external source. External source provides the high magnetic field. This is very less, and its intensity is very low. This is what I want to explain you in the previous slide. When the two coils or just two aluminum foils, in this case Coils means two solenoids are bring each other, they will experience a force of attraction or repulsion. Two magnets are brought near each other, they will experience a force of attraction or repulsion, their magnetic fields of line will be disturbed. And this is the illustration of the previous slide. Suppose we create a structure like this. This is the just a wood support here, and if I just made aluminum foil strips here, and this the path of the current is just by passing through this first aluminum foil, and then it is connected from the base, and then it means that current will start flowing through the second coil, and then it will just left off this coil and entering from this point and leaving through the other coil. So if I just try to turn on the switch, this is the aluminum coils can experience a force of attraction or repulsion because they are placed very close to each other, and also they are very thin. And suppose I turn on the current, and the current start flowing from the first coil, aluminum foil, and the direction of the current through the first foil is downward, while you can see that the direction in the second foil is towards upside, and it means that they will experience a force of repulsion between each other, and you will see that they bend across the outside, and they are trying to get away from both each other. So this means that if one current is downward and other is upward, there is a force of repulsion between the foils. Another case when the both currents are flowing in the same direction, here you can see that the pattern of the pattern is changed, and the infrastructure of this equipment is changed a little bit, and now these are connected with the same source of the upside and the same downside. It means that the if I supplied entering point is this one and the leaving point is this one. Currents, when I just turn on the switch, current starts flowing from the first coil, and the same current will start flow to the other coil because these are connected in parallel, and the current has two paths. Now current will be divided, and the same current, the direction of the current will be the same. And when the same currents flow, here is the different case is needs we saw a different case this time. Both coils are going to attach with each other, and this means that whenever the same currents either in this direction or the both current in the opposite direction, but the both currents direction must be same with respect to each other. This doesn't mean that either they are upward or downward, they feel a force of attraction. Here we need to introduce a new rule that is called right hand palm rule, where we need to use the palm of the hand and fingers and the thumb. So this must be right hand, don't forget that. You do not take consider of the left hand. We already introduced another rule in the previous lectures, and that was basically right hand grip rule, and this is right hand palm rule. We are not going to turn the fingers around and make a grip of the solenoid or a coil or a just wire. We are just considering the our fingers and not going to tilt them anymore. Just take a look at this example. For example, current is flowing towards this side. It means suppose according to the conventional current, positive is here and the negative is to the other end. Current flows through this way, field is downward, and if we just trying to make sure our fingers are in the right direction of the field and they are downward, I cannot show you here my fingers because there is no camera attached here in this recording. So suppose that my fingers are downward. You can also do it by yourself for the complete understanding. Just place your fingers with the screen downward, and thumb must be in this direction. From positive to negative means this side, your thumb must be towards this side. Then your palm will be towards your face, means that away from the screen. And this is the z dimension or 3D, and I cannot basically try to show you here. And this is the current when current is inward. When the field direction is changed or the current direction is changed, one of them is changed, then the force will be inward into the screen. These are the basically 4 cases, and you can try the other cases by yourself, and these are very interesting cases to try, but the time is limited. I am not going in details of these further cases. This is the formula that is developed for this understanding force, for calculation of the force that is placed under the influence of the magnetic field, and and current is also supplied and passing through it. F is equals to I L B sine theta. Here theta basically represents the angle between the magnetic field and the current. Going back to explain something more, suppose that your thumb, this is your direction of the thumb, and it will represent the current that is flowing across the any conductor. Maybe the conductor is wire or something else. Let's suppose it's a wire and the current is flowing, and the direction of the current is just represented by your thumb and the fingers. If this is the ideal case, that the fingers must be open. Although the fingers can be tilted, and for example, this is the magnetic field, you can change the fingers, but the ideal case here, if the whatever the direction of the field, you just move your hand but do not tilt your fingers. This must be straight and full open, like here, this is this one, and point the direction, point out your fingers in the direction of the field, and this is the direction of the field, and this is the direction of the current, and there must be angle that is the 90-degree between the field and the current. And this is the case that maximum force, this is the case for the maximum force. Whenever we are going to change this angle, for example, here bending our fingers and the angle is less than 90, we are basically reducing our force. Maximum force can be experienced when the angle is 90. So when 90-degree we experience the maximum force, that's why we use the sine theta. Sine theta shows a maximum value at 90-degree, so it means that sine 90-degree is equals to 1 and sine 0-degree is equals to 0. I is the current, B is the magnetic field, L is the length of the conductor in the magnetic field. F is equals to ILB sine theta. Sine theta, I just this is the same picture I just added here. If the magnetic field and the current are at right angle to each other, theta then is equals to 90-degree. What I explained you in the previous slides, this is what I write here. F is equals to ILB. Then this formula will become F is equals to ILB when the force and the field are at right angle. Then we can just replace our formula with this, because when sine 90 it is equals to 1 and 1 can be written or not, ILB is multiplied by 1 means ILB, so don't need to write sine theta. In other words, I can also write I cross B. It is clear from the equation that the force is maximum when the conductor or the current is at right angle, is very important, right angle to the field, and is 0 when they are parallel. The right hand rule can be used to find the direction of the force. If the fingers are pointed in the direction of the magnetic field and thumb is in the direction of the current, then the direction of the force is out of the palm. And these are the just what I explained already, and this is what I write it for you. For example, sometimes I forget to explain a point. That's why I write it here to remind myself during the lecture. And you can also read these points by yourself when I provide you this lecture, and that's why I added some points here. There is also a magnetic field associated with the electric current I in the conductor, but this is really small compared to the applied magnetic field. This is what I already explained in this second slide. And this is the illustration of something new, and that is the force here. Force, direction of the force is the same, that is the direction of the current in the conductors. This is the positive negative, current is flowing also in the same direction, field is also in the same direction. The angle between the both of them is 0 degree because they are parallel. The angle between them is 0 degree, which means that force is 0. There is no force acting on this in this conductor right now. You can also try out this one and illustrate either it is okay. How I can say that there is no force acting on this coil although magnetic field is also present here. You can try to understand this with the help of just the right hand palm rule. And there is another case where the magnetic field is not from left side to positive side, sorry, left side to right side, and here the case is changed. The magnetic field is just represented by cross and dot. There are the two different things to represent the magnetic fields or electric fields on the paper, that are the two-dimensional, and to represent and give a look on a 3D. Cross basically means that something that is coming something that is going into the paper, the direction is into the screen. If I represent the dots and I circle them, it means that something that is coming out of the paper. Cross means that this is something going into the screen. Here the cross is used, it means that the direction of the magnetic field is into the screen. Just try to do this while you are listening. Point the thumb of the right hand into the screen and turn your fingers towards the direction of the current. Then what do you think that you will experience a force, and the direction of what is the direction of the force here? Your fingers are just into the paper, and that your thumb is into the direction of the current, and your palm is pointing out upside. So this is the actually right. These two figures you can try out by yourself because time is already, I take too much time in this episode. Okay, this is an example, very simple and very good example, interesting example. A wire carrying a current of 3.4 ampere. So current is given, and note that it is given in ampere, so we do not need any efforts to convert it into ampere because it is already given in the standard form. This is the wire that is carrying the current, and it said that it is given that it carries 3.4 amperes of current and placed at right angle. So another important thing that author in the question given to me, that it is placed to the right angle. So it is understood that the sine theta we cannot write, or no write is the same thing, because sine 91, so I do not write in the formula sine theta here. Okay, to a magnetic field of strength, this is the strength of the magnetic field, this is the magnetic field, and the strength of the magnetic field is 0.2 Tesla, and also given in Tesla, so it is in standard form again as shown in the figure. This is the figure I'm already explaining in the parallel side also as I read the question. Calculate the magnitude. First we need to calculate the magnitude. Magnitude can be calculated with the help of formula. And direction of the force. Direction of the force can be calculated by using the right hand and palm rule, what we had discussed in the previous couple of slides. And the direction of the force on the wire if only 0.8 meter of the wire is perpendicular to the field. This is interesting thing, that the length of the wire is 0.8 meter. We are not considering the extra length. If for example this wire is long, and also from this side too, this wire is carrying on to other things and other appliances connected with the battery source or whatever, but we are just trying to consider in our example only the length that is under the influence of the magnetic field, that is with the perpendicular to the, that is at a normal at a 90-degree angle with the magnetic field. So we are just considering this length that is influenced or affected under the magnetic field lines. If there is a huge length, suppose I make this question a tricky question, I just said that the total length of the wire is 2 meter and 0.8 meter of the length is influenced under the magnetic field perpendicularly, and calculate the magnetic field. So you student might confuse that what length we are going to use, the 2 meter or 0.8 meter, or just we can have to subtract 2 meter minus 0.8 meters, it will be 1.2 meter or something else, the negative thinking and the this is the misconceptions in your mind. Don't avoid these things, because we need to consider only this section that is under the magnetic field of the wire. It is perpendicular to the field. The rest of the parallel is to the field and can be ignored. Okay, so F is equals to 0. F is equals to, because here the force is 0. This is what means F is equals to, at this point force is 0. F is equals to ILB, and just pointing out putting in the values 3.4. What is the 3.4 means? The 3.4 means that the current 3.4 ampere. L means length is 0.8 meters. I'm just putting the values. What is the strength of the magnetic field? It is 0.2 Tesla. That is, substitute these values, the answer is 0.54 newtons. Okay, very good. The direction of the force is given by the right hand rule. So just point out here, I'm just trying to make a diagram here, though I'm not good by drawing with the mouse. Okay, suppose this is your thumb, and thumb is pointing in the direction of the current, that is upward, and this is your fingers, and fingers are pointing in the direction of the magnetic field, and the palm is the other side of the palm is the others, because this is right hand, so the palm is to the other side of the towards the screen. You cannot see the palm here. Okay, and this is the direction of the current. This means that the force is into the paper. I can also represent the force into the paper with the help of just dots. That means that with the help of cross, which means that these are going into the paper. Okay, a second case, the wire is now placed so that the current is in the direction of the field. Wire is placed so that now the field direction is same, but the direction of the wire is also changed, and it is now making the angle 0 degree with the field, because it is placed just parallel. When the angle is 0, it means that sine 0. You know, the complete formula of this is not the complete formula. Complete formula is when we append sine theta also with this formula, then it becomes a complete formula. We ignore this here because sine 90 is equals to 1, and when we have to consider this here in this case, because this is not parallel, and we have a theta. When sine theta is equals to 0, sine 0, it will whole term become 0, and when 0 multiplied with this one, it will also be 0. So the force is here 0, because theta is 0, hence the force is 0. Note that when the current is parallel to the field, no force acts on the current carrying wire. So how can we find the direction? So we cannot find the direction in the second case. This is a question for you, and that is the end of episode 9. Further discussion will be continued next time. Try to figure out this question and make sure to answer this question in the comment section, because this is very easy question. Take care. Allah Hafiz.